need to do a lot of things in terms of classification tests. And the thing is, even though it was designed as a linear classifier, it's good for most of problems we are facing, because even if you have problems that cannot be classified linearly, you can transform your data space from low dimensional space into a higher dimensional space. So maybe your data cannot be linearly classified, but when you transform into higher dimension, properly you can classify it using a linear classifier, like a Perfecto machine. And we did talk about well, what we call the kernel trick. And if you remember, we don't have to explicitly transform our data from low dimension into high dimension. We actually just need to define how do we calculate the dot product in a higher dimensional space. And that's why we call that a kernel trick, right? And so today we are doing something very different. We are doing the task that compress your data from high dimensional space into a lower dimensional space. And we are talking about dimensionality reduction. Well, for a lot of people here, you guys may know about it as a technique for uh, well, visualizing the data. But we can go more than that. Actually, what happens is you can use this technique not just for visualizing, but somehow can help you to reduce the complexity in the data. For example, if you have some sort of image like this one, right? And let me talk about the digit number classification task, for example. You may have a lot of number O, right? This one, and you may have one, and one, and one, and one, and two, and two, and two, and three, and three, and three, four, 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 five, 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 six, 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 seven, 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 eight, 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 nine, 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 nine. So as you are observing, what you see is that in the image I'm providing you, not every position in the image has information that's useful for classification. Those area, maybe this, okay? And what we care is that those area actually provide no information for classifier. And then, if it is possible, we can reduce the dimension of our input. Let's say your input is 100 by 100. It turns out that you have a vector of 10,000 dimension. And that's a lot, right? But if you perform some sort of dimensional reduction, you may reduce your input now into like just 1,000 sample. And then you can also do the same classification task with no problems. Well, when we talk about dimensionality reductions, we are going to discuss two aspects of dimensionality reduction. You may intend to use dimensionality reduction for classification, but you may also intend to use dimensionality reduction for, well, representing data in another form. You may heard about some sort of ideas like word embedding, or you may heard about something like character embedding, or you may heard something like image embedding, for example. all kind of things like that will be some application of dimensionality reduction. But well, the fact is, those techniques are much more complicated than it looks like. So I'm going to walk through every concept one by one. Don't worry. Okay. So let's see. I can start with the agenda today. We are going to review a little bit on metric calculus first, and then we will talk about LDA as well as PCA, and finally, we may discuss some extra techniques like Disney. Okay, those may be useful for you guys in the long run. Okay, so let's start. I think this part is not hard. It's just something I believe we need to review before we go any further. Okay, so let's talk about metric calculus. You may heard about dot product in matrix notation. So that's nothing new for you guys. I can skip this one. The dot product between one vector with another vector is also the product of a transpose vector A multiplied with B. Okay, that's normal. You have a projection of a vector A onto vector B, for example. This is A and this is B. So the projection of A onto B is something like this one. So it's gonna be on the direction of B, but B should be normalized by dividing by the norm of B. And so R here actually the length of A. So what is that R? R should be equal to A dot product with B divided by B. Okay, why? Because I guess you know it, A multiplied with B is a dot product. It's equal to norm of A, norm of B, cosine between A and B. Okay, so this one is the cosine between A and B. That projection is actually, that projections we are talking about is actually A multiplied with cosine between A and B, right? And so it turns out that you got A1 is a projection equal to the dot product divided by B, okay? Oh, sorry, that R. R is the length, okay? So this is R, all right? So R is actually the dot product divided by B, the length. And A1 is the vector along B direction. Therefore, you have R multiplied with the normalized vector B. Okay. By the way, we have to remind something about the duration. So when you take the derivative of some vector, you may encounter that derivative of a vector with respect to another vector, that is a matrix, right? Because now you have to calculate the derivative of yi over xj, this one. Derivative of yi, the component I of vector y with respect to xj, the component of vector x. And so we have a matrix. It turns out that you can also have derivative of a matrix or over a vector. You can also have a derivative of a matrix over another matrix. That's your choice. But well, if you have derivative of a matrix upside m by n, and the vector x has the sign d by 1, you should have this derivative with the sign like m by n by d. is a tensor of three dimension. Likewise, you have M by N matrix, and if you take derivative with respect to another matrix upside K by L, then you probably have a tensor, 4D tensor. Those 4D tensor has the dimension M by N by K by L. Okay? So overall, we understand that taking derivative of a matrix, a vector, or even a tensor with respect to another vector or another matrix, that's not so hard. It's just how you representing that one in a high-dimensional tensor. Okay, and that would be easy. But that's just in theory. In practice, we do not encounter such kind of thing. Well, there are some propositions that you may want to remember because this is going to be useful in the long run. For example, you have a term like alpha equal to xt multiplied with a matrix A multiplied with x. So xt is going to be a vector like this one, like d by, sorry. Xt is supposed to be 1 by d. A is supposed to be a matrix of d by d, and x now is another vector of 1 by d. Therefore, you will have alpha now is 1 by 1, which is a scalar. Okay? So, taking derivative of this scalar with respect to a vector x gives you some sort of ideas like xt multiplied with a multiplied with plus with transpose of a. Well, it's not hard for you to prove this one. You can actually compute this easily by doing some sort of calculations. Well, should I do it? Should I do it? Well, if you want to prove this one, it's in the metric calculus, by the way. So suppose that I'm talking about this product. So let me check the element j here, okay? And that z equal to xta give me j equal to the sum over I equal 1 to d of what? Of xi and a of row I and column j. Okay, so this is this is j zj, and then you have z multiplied with x. That gives you a value which is the sum over k from 1 to d of z k multiplied with x k. So this gives you, if you replace things, you will have the sum over k equal 1 to d of xk and multiply with the sum over I from 1 to d of xi a I k, right? Okay, so given this term, now you already have, this is alpha. Now if you take the derivative of alpha with respect to, well, x j, for example, too many subscription, and that make you feel a little bit confused, I suppose. So what it turns out, well, it's a vector, right? So I'm just checking components of that vector. So if I take this derivative, then it's gonna be what? Uh, well, if you break down the formula on the top, you will get uh, okay, I and K, both I and K run, right? Both I and K run. So it turns out that you will have XK run as well as I run. Hmm. Okay, so it's gonna be it's gonna be something like the sum over K and the sum over I of xi x k a I k. And if you take derivative with respect to xj, you will have what is this? You have to index, right? So hmm, it's gonna be 2 a aij plus aji multiply with x, right? So if you breaking down this one over terms, you will have something like the one you are seeing over here, because now you are going to have xi equal xj and xk equal, sorry, I equal j, give you xk, the sum over uh, no, sorry. The sum over, let me check k. Sorry. What is that? Okay, sorry. There's something. Okay, forget it. I think there should be no phone call now. By the way, if you take derivative like this one, so I'm going to have the sum over k of x k a j k plus the sum over I, sorry, sum over I of x k, no, x I a j k, where, no, sorry, my bad. This is a I k. Well, if you write things this way, then what you observe is that you are going to have this term and this term. Well, this term gives you a vector, right? And this term also gives you a vector. So the component xj now turn out to be x multiplied with a, okay? And this turn out to be xt multiplied with at, right? But I'm talking about the component j. And so this gives you the formula over here. All right. So that's explain a lot about what we have. Well, you don't have to prove those things. I just tell you that there's something you learned in metric calculus before, and actually not so hard to prove those things. From now on, you guys can use this result for your work, but remember, you need to know how it works first, okay? There's another proof here, which is much more shorter, I think, because I did prepare it in hand before this. So anyway, that's easy. By the way, If the matrix A is symmetric, of course, that derivative turn out to be 2xta. And that would be awesome because now it turned out that we are talking about some quadratic function, right? And there's another proposition here. Well, in case that matrix A is symmetric and of course it's square, then you have the relative transpose equal to what you are seeing here. Now, there's something about metric calculus that you have learned earlier. That's called eigenvalue and eigenvector. So those value and vector are special because when you multiply that vector to the matrix A, that result in another vector with the same direction of the vector v, but was scaled by some factor lambda. And so if a vector v satisfies that criteria, that vector v is called eigenvector. And that constant, that scale vector v, is called eigenvalue. And we learned about this a long time ago. Now, in order to solve this one, you may encounter some equation like A subtract with lambda I V equals 0. And this, if you want to solve, the trivial solution, of course, is V equals 0. But we don't care about trivial solution. We care about some other solution that give us a vector V that is different from 0. Well, how to do that? That solution appear only and only when V and A subtract by lambda I is special. So we are talking about determinants of A subtract by lambda I. If this is differs from 0, then of course you will get the trivial solution 0. Now if this determinant is equal to 0, then V is different from 0, and in that case, when you solve this equation, you will get lambda, which is the eigenvalue. And from this lambda, if you submit it to the function and solve V again, you will have a family of vectors. And the basic vector you get will be the eigenvector. Okay, and we don't have any trouble with this one. We can do it all day. Okay, so this is another example, and I think those example is not hard. It's just complicated because you are working on a 3 by 3 matrix. So if this is a 3 by 3 matrix, then calculate the derivative. Calculate the root of this equation is not trivial. It involved in a an equation of degree 3, I suppose. That's right. And so I'm not going to solve this one right now on the class. It's just too much. So you guys can try it at home. Actually, we have some other case that easier for us to calculate. Maybe if the matrix A is of the degree 2, then it's easier, right? So anyway, let's uncover the matrix like 19 subtract by lambda, 20. This is 13 subtract by lambda. This is 4, 20 minus 16, minus 16, minus 4, 31 subtract by lambda. So if you take the determinants of this one, I suppose that you can get it. This will be 19 subtract by lambda multiply with 13 subtract by lambda, multiply with 31 subtract by lambda, subtract with 16, and then you have to subtract with 20, and what you have inside is 20 of 31 subtract with lambda, subtract with, oh no, plus 4 6 24 64, like this, and plus, oh, let's give you 16, right? Yeah, that's right. So I'm going to have minus 16 of, well, a subtract with 16 of 13 minus lambda, something like this. And of course, you can say that if you extend the equations a little bit more, you will end up with the equation of degree 3. You can solve it. I'm not saying you cannot, but this is tough for for me to calculate it without knowing the root. For computer, we often write some iterative algorithms in order to probe for the solutions. But anyway, in this case, suppose that I know lambda is the 27 is a root, then I can somehow reduce this equation from the degree 3 back to degree of 2, and then you can solve the two other root. Anyway, if you have lambda, you take it back into the equation, you can compute b. That's no trouble. Okay, so that's it for the eigenvalue and eigenvector. Now they implement those things in library for a long, long time ago. So all we have to do is using it, but you have to understand how to calculate. Now, this case is easy. In this case, you have a simple matrix of 2 by 2. It's easy for you to find the determinant, which is the quadratic equation you see over there, and you can easily get the two root value, lambda 1 and lambda 2. Okay. I'm not going further with this material. It's very time consuming, but you already know about. We have another proposition. It's the if A is a symmetric matrix, then there's something important that you have to remember, that all eigenvalues are real. Remember, it's real, because in theory, when you solve for the root of the equation, you may end up with some complex root, and the complex root is good if you compute it for some analysis, but in practice, we only concern about the real root. Okay, we don't care about complex number. So if you have some symmetric matrix, then it's good for you, because you always get the real eigenvalue. And therefore, from this, you can get an linearly independent eigenvector. That is good, right? And remember about, let's say, EI is an eigenvector with respect to lambda I. Okay, suppose that EI is an eigenvector with respect to lambda I. Then what you see here is that what is linearly independent? Linearly independent means EI is, well, what can I say? Okay, it goes like this. There is no way you can find AJ there's no way you can find AJ. So that EI equal to the sum of AJ EJ, with J differ from I. Do you know what it means? This say if for some reason you are trying to have EI to be a linear combination of other vector, other agent vector, then it say there is no way for you to compute those weights AJ. It cannot be, right? So this is why we say those agent vector are linearly independent. And it's related a lot in the theory of metric calculus, and it's very useful for us in the long run. So keep that in mind, okay? All right, so let me move on to another word. So there's another proposition which is important for you guys. It's say if you have a matrix A, and from matrix A you can find an agent vectors that linearly independent and corresponding agent values, you can decompose the matrix A into PDP minus 1, where D is a diagonal matrix and each value in the diagonal is agent value, where P is the matrix where each row are the agent vector. Okay, and here is the proof. It's kind of a little bit complicated, but not so hard to get. So what you get here is that P invert of P multiplied with AP equal to invert of P multiplied with A and OV, right? You can multiply A with OV and then you get over there. So the tips is that because V is the agent vector, so you will get this agent value. And as you have this, you multiply P minus 1 into the vector inside, into the matrix inside. And what you get is this one for the first element, and this one for the second element, and so on. Okay, so the first one gives you lambda of E1, okay, where P minus 1 multiplied with V1 is E1. And if you keep doing so, you will get what you want. This is the diagonal matrix, lambda 1, lambda 2, and lambda n. Okay? And why this conclude our proof? Because if you take a look at this one, I can multiply this with, let's say, what if I multiply P minus 1 with A, and then I should have P minus 1 with P here. Those things will be the identity matrix, of course. And then if I multiply P with A over here, I would have P over here. And this is also, this is also another identity matrix. So you should get this one give you P minus 1 AP equal D. Okay, so this is why you have something over here like this one. Okay, given another example here, you can easily verify what we are talking about. So no trouble, right? Now, first, let's talk about LDA, which I think the simplest one to be uncovered. Well, LDA stands for Linear Discriminations Analysis. Now, the word D means discrimination. So it means you are trying to find a linear projection to support that classifier. Okay, you are trying to project your data onto a lower dimensional space, but the purpose of that projection is to have the classification process. I don't know much about your classifier, I don't care. But what I want is when I project my data onto a new dimensional space, it helped me to classify data. Okay, so for example, I have some data like this. Suppose that I have some data of class A, like this one. I have some data of class B, like this one. Now, there are some way for me to project data. I may intend to project data onto this direction. Okay, so I may have my data of class A end up somewhere here. The data from class B end up with somewhere here. Okay, so for this one, I can easily get the classifier, which is some sort of line like this one, and this is the cutting point where it helps you to classify the data. But it comes with a risk because now the data on both class, when you project onto this dimension, they are close by each other, and that means there's some error in the classification process. Now let's say I'm choosing another the projections, let's say here. Then my data, when I project onto this dimension, this is where I have the data of class A, and this is the data of class B when I project onto this dimension. Okay, and so now what you observe is that I can also find the, well, I can easily determine the classifier like this one. This is the cutting point. However, the good thing about this one is the gap between two class now is bigger, just like a vector machine, you know. So if I want to project my data for the purpose of classifying them, then I would choose the orange line over the green line. Okay, and that's the purpose of LDA. We are interested in finding a projection of data so that your data are helpful for classify for classification. Okay. All right. So look at this example. What do you see? Well, if you see the mean of the class A and the mean of the class B, now when it projects onto the new dimension for the orange direction, you will see they are far from each other. For the green one, you see that they are not so far from each other. So the core idea looks obvious, right? We are going to project our data onto a new dimension. I hate it. I'm sorry. If that bother you, but the noise outside. They're constructing something. Our university are in the process of constructing. Oh, it's so annoying. Sorry. I try to find a room for teaching, but ah, that's no good. What can I do? Okay, sorry. Let's focus on what we are talking. Okay, I'm sorry for the noise if you heard it. All right. So the first principle here is that we are interested in separate the distance between two class of data as far as possible. Okay. So some people may argue, why don't we just project our data onto the same direction of me one and me two? So let's say I have this one is me one, which is the mean of the first class. This is mean two, which is the mean of the second class. Why don't we just project onto the direction of mean one minus mean two? Why don't we do that? Because there is another criteria that we are thinking about. When you project data, you not just want to project data onto the new dimension that make the distance between them bigger, but also you want to reduce the variance of the data. For example, if you project the first class onto this dimension, the variance is small, right? But if you project onto this dimension, the variance is high. So do you prefer a low variant or high variant? Of course, you are going to prefer low variant because when your data focus and distribute nearby the mean, then it's easy for you to classify them. Okay? So the core idea here is max. Okay, no, I should not write this. So LDA give you two criteria. First, max distance between two projected mean. Okay, and second, we want to minimize the variant or covariant of the projected data on sorry, on each class. Okay, so these are going to be two criteria that we are going to follow. Now let's try to derive some formula. Okay, hopefully we can get it easily. So these are some note on the projection, so you guys can check it out later. That's just something I mentioned earlier. Okay. All right. Let's see. All right. Here in the material, you can see that we are talking about some feature that's invariant, which means they are not so useful for classification. For example, observing the data like this, you see that the data has two values, x1 and x2, but x1 seems to be unchanged. In other words, the value x1 turned out to be insignificant. It's not so useful for classification. Now, in order to classify the data, may you rely solely on x2 rather than x1. Okay? And this is why we say that we don't want to work with the data with low variance here in the classification process. Anyway, um, now we mentioned about LDA for a lot of times from beginning. Now, what you see is that we intend to project the high dimensional vector onto a lower dimensional vector where the between class distance is maximized. That exactly what I mentioned earlier. This criteria, the maximum distance between two projected mean, and the within class variance, the variance inside each class is minimized. So when you project the data, you want your data densely distributed nearby the mean. Okay, that's the idea. So when it comes to formula, what you see is that you can easily have the projection. Let's say um, you have x is the data, the original data. Then you may project x into the new dimensional y. Let's say y equal to wt x, okay, where w is a projections, right? And as you have this one, then what about mean? So let's say mean of class 1 equal to the sum over xi, where xi belong to class 1. Then the projected mean, or should I say some other word? Or okay, let's say mean of y1. The projected mean turn out to be, well, same thing. Y wt of the sum over xi, what xi belong to the class 1. So that equal to the wt was mean of class 1. Okay, and so here is the new mean. This is the old mean, right? And the distance between two two groups of data now turn out to be d equal to mean, sorry, mean 1 y subtract with the mean 2 y, which gives you wt of mean 1, mean 2. Okay, so this is the projected distance between two classes, and you want to minimize this thing. All right, that's the first concept. But remember, this subtraction, of course, this projection may not give you the positive number, maybe a negative number. So you have to think about it. So here is the mean vector. We use m instead of mu over there, but they're the same, don't worry. And the mean of the projected data is here. So the distance we're interested in minimizing is the square of the distance. So if you want to maximize this one, then you can just take derivative, right? But not yet. We just end up with the square distance, okay? And let's talk about the variant. So the variant of the data inside a class will equally to, this is equal to the square of ym subtract with the mean. And what we want to minimize here is the total variance of each class together. Okay, and this is not so hard, but it poses questions. If you rely on this formula, what happens? Well, if you interested in this sum variant and you want to minimize this variant, the problem is you are treating your data in a way that may cause some sort of bias, and that may be a risk. So have to be very careful here when you derive the formula. Why I'm saying this? Because We are talking about algorithms that based solely on data. So the more data you have, the better. But if, let's say, the class A only have 10 sample and class B have like 1,000 sample or even 10,000 sample. So this is some sort of imbalance inside your data, the bias in your data. And so the variance now mostly favor the class with more data. Okay, if you divide or take the average, if you take sk square equal to 1 over volume of ck of sum over y and subtract with mean k square. If you do so, then fine. This is like the variant, but it has been normalized because you take the average of variance. Okay, but now what you see in this formula is not the average, it's just the total variance. And if you rely on this, you have to be aware of the bias. Okay, see what I'm saying? If you are having two classes and one class has more data than the other, then the variance of the class with a lot of data may be more important than the other class, and that is not bad. I'm just saying it may not fair in the evaluation and in the projection. So think about it. What do you want? Do you want to treat them fairly, or do you want to treat them depending on some bias in the data? Your choice. Okay. So in the beginning, most of people they don't really care about it, but they only concerned about how do we calculate the variance. Okay, and let's say our data are equally distributed, they have very little of bias, then this one is fine. All right. So given that, what we end up now is the Jacobian, the function to be maximize. So you want to maximize the distance, but you want to minimize the total variance. Therefore, you take the distance divide by the variance. So you max the top, you minimize the bottom. Okay, and you may interested in representing this formula in a simple form. So we define some sort of thing called the covariant matrix. This is the between class covariant matrix, and it's measure the covariance between two class together. It's we call SB, and we have another covariant matrix called within class covariant matrix SW. So you have SB over here and SW over here. The formula is there. You can calculate. It's just a little bit worry, but you can do it. I trust you. So you have to take some calculation here, right? And as you have SB and SW, the Jacobian matrix now turn out to be this one. And this is interesting because now we are representing our function in terms of the matrix form. And if you take derivative of J with respect to W, you know how to calculate W. Okay? And without any other explanations, I guess that derivative of J with respect to W equal to 0 give you, well, the 2 to what? WTSB, right? WTSB, is that correct? You can also write SBW, your choice, or multiply with WT as W okay, and subtract by 2 of Wt as W multiplied with Wt as Bw. This is 0. I only need this. And if this is the case, then it turns out that you will end up with the solution for W, and this solution is a closed form solution. Okay. Um, I don't think it is hard, but it's require a bit of thinking before you do anything else. So here is the detail. You may interested in twisting around with the formula strip that from left to right and then doing some magic by discard W and discard some other thing. So in the end, what you have is this one. First, uh, this SPW in the direction of M2 minus M1 and W in the direction of SW minus 1 of M2 minus M1. What it means, if you want to calculate projection of your data, all you have is calculate the mean of plus 1, the mean of plus 2, and you have the mean of M2 minus M1 here. And you multiply with as W invert. And then you will get the projection vector W. This is W. So W is not necessary to follow the direction of M2 minus M1, but it can be modified a little bit by the matrix as W. Okay, so they what can I explain about this one? It's just that simple. Okay, the value of W is not important. The direction is more important. You can scale W by any factor. That's all right. It doesn't matter. All you have to remember is the direction. Okay, so you can normalize W if you want to, or you may turn W into some shorter form or easier to read form, whatever. I only care about the direction. Okay, and you can project your data onto W just like that. Now let's talk about another technique for dimensionality reduction in machine learning. We call this one PCA. PCA stands for Principal Component Analysis. So the word principal means you are going to take the data that most important to you, the principal. Okay, you only take the data with the principal value here. Now let's see what is the principal components. You can observe the data distribution here in 3 dimensions, and you see that it looks like your data are distributed on a plane or maybe another hyperplane. And what you interested in here is, can I project my data onto a lower dimensional space that's still preserving the data I have? In other words, I want to project my data onto low dimensional space that still keep the representation of my data. So here, there's something different. Before that, when we talk about LDA, we are talking about a projection that help us to classify. Now, these projection techniques help us not to classify, but to preserve the representation of the data, the distribution of data. You want, in other words, compress the information from high dimensional space onto a lower dimensional space. Okay? And here is some information you may want to consider. First, we may interested in taking the mean of the data. Of course, the mean is very important. It tell you what is the center of the distribution, right? And then you may interested in calculate some sort of variance of the projected data. So when you project your data onto the new dimensional space, you would like to observe the variance of your data on each dimension. Okay, and that turns out to be the formula you are seeing here. UT xn subtract with UT mean, that is the variance, right? And you are giving it some sort of formula, and you can easily take out the, well, what can I say? You can easily take out the covariant matrix S over there, and the covariant matrix turn out to be xn subtract with m multiply with xn subtract with m transpose. And don't forget that this is the column vector, and this transpose turn out to be a row vector. So this one gives you a matrix, n by n matrix. Okay, don't forget it. So this is called covariant matrix. It's measure the covariance between two-dimensional. Okay, now we are interested in maximize the covariance instead of minimize. Well, is this differ from the LDA? LC LDA before. Okay. So this is different because now when you try to project your data onto a lower dimensional space, you want the variance is higher than any other method. I mean, we want to make your data spread out as much as possible on the new dimension rather than make them gather around the mean. Okay, so for LDA, you're interested in minimizing the variance, but for PCA, you are interested in maximizing the variance because as your data is spreading out around the mean, then it's easy for you to preserve the information of your data. Okay, so that's the basic principle. And given that information, now we are doing the optimization problems. We are looking for a way to maximize the covariance on the new dimensional space with respect to with respect to this one. And this is the optimization problems you see earlier. We can use Euler-Lagrange equation to solve it, right? And this constraint saying that, okay, that projection U is just a unit vector, okay? So you are projecting your data onto the new dimensional space by U1, and that U1 is the unit vector. That's it. And so we end up with the Lagrange equation like this one. And as you know, we can easily end up with this solution. It's not hard for you to rewrite it. It's just very simple. When you take derivative of the Lagrange equation, let's say you have L equal this one, then derivative of L with respect to U1 equal to what? 2 UT as what? Plus or subtract? Subtract with 2 lambda 1 U T. And that gives you exactly what I'm saying. Instead of writing UTS, I can write as U1 equal to lambda 1 of U1. Okay. Oh, I don't have T here. I don't have T here. Yep. I don't have T over there. Oh, yeah. That's right. That's right. So this is exactly what we end up. This is something you may see. Lambda 1 is the agent vector, agent value of the covariant matrix S, and U1 is the agent vector of the covariant matrix S. And you can easily calculate this one. No trouble, right? So remember that and you can do well. So again, for PCA, you are going to somehow select some agent value with respect to some agent vector that you interested in when you try to project your data. And the thing is, you must or you are going to choose some dimension that has the highest agent value. In other words, you are going to pick the agent value with respect to the largest, you are going to pick the agent vector with respect to the largest agent values. I'm sorry because the word is messing, but anyway, we are going to pick up some dimension that has the highest variance. Okay, and because of this, we can preserve most of our informations. All right, so think about it's like if you can decompose your data into this form, we can think about that as a way to compress our data. Let's say your original data can now be approximate by a loading and components. And thus, if you take the products of loading and components, you can try to reconstruct the content of your data. In other words, you can actually reconstruct the data on a lower dimension using the data on the high dimensional space. Anyway, that's the application. It's like you are trying to compress the data. Okay, and I don't see a lot of people use PCA for compressing data. It's not making any sense. You know, PCA actually is used for projecting data, reduced dimensional data for mostly for pre-processing, because some of our data may be very irrelevant. So people want to discard those data that is not relevant to the problems and trying to go from there. For example, you have the the health information of some patient, and in that sheet of information, you have like 1,000 of numbers, the glucose, the HB, SGCA, so many factor. I don't remember exactly, but there's so many things in that sheet. And if you are doing some job like collecting data of people who got diabetes, then most of all the information are not so relevant. So when you do the data projection, you interested in finding a shorter representation of your data, then you may use PCA for that projection, because irrelevant information may be discarded at the beginning of the process. Okay, and you may use that data on the lower dimensional for some better classification, but later. All right, and there are some application of feature selection and text classification that you guys may want to take a look at. Um, I think that I'm going to go quickly on this part because it's very simple and not so many people are using this technique nowadays. It's like something outdated, but I'm keeping this slide because of the history of the course. Anyway, why this matter? Because well, the text feature actually very high dimensional feature. We we know it, and it's hard for us to use those feature in the raw form. You have to somehow pre-processing it and reduce that complexity before you go any further. The second idea is that we may encounter some sort of noise in the data, and so using PCA for reduce the dimensional of the data is useful because now you can discard a little bit of noise in your data. And that is also good. So, in text classification problems, we have several ways to representing the document, like using the back upward, or just second upwards, or may we use some sort of some grammar and semantic elements inside, but I don't see a lot of people use it nowadays. It's like something very weird to use. I can either see them using the back upward, which is also outdated, or the second upwards, just second upwards. Now, some other people may interested in using the probabilistic distribution of topics, or may you call it topic modeling. Let me explain a little bit on topic modeling, what it is. Topic modeling means you are trying to put some topics information on your document instead. For example, if you go to VNS Red and you read an article, that article may be classified into the social article, but also that one can be related to the sport. It can also related to politics a little bit. So topic modeling means given that article, I would like to see what kind of topics it belongs to. So I may get the output to be a vector of some topics, and like it has 80% relevance to the social topics, but only 10% related to sport, and also only 1% related to politics and something like that. And that what we call topic modeling. Okay, you're trying to extract some information from the document, and those information is the topic information. All right. So in order to represent um, a document, you may use several ways depending a lot on what problem you are trying to solve. Okay, and there are some sort of pre-processing techniques that you guys may concern when you work with text classification. And most of those tasks are very outdated too. For example, they say that you have to remove some stop word. What is stop word? Like the full stop or conjunctions or prepositions, something like that. We call it stop word. it serves no purpose in the meaning of the text. But I don't totally agree because when you miss a comma or when you miss a full stop of a sentence, then the meaning of the whole sentence may change. So the basic idea here is, may you remove the stop word. That means you don't concern about the context or the meaning of the sentence, but only care about the appearance, the sequence of word appearance. That's one thing. However, I still believe that removal of stop word is not a very good idea. Of course, in the old day, like 20 years ago, this one may work because you don't have deep learning in hand. So doing this may reduce a lot of complexity in your data and it's helped you a lot. But nowadays, with the advance of neural network, especially deep learning, we try to preserve some information in our original data. Even a full stop of a sentence or a comma may change the whole meaning of the sentence. So beware of that. The second processing step that people may interested in doing on your text is called steaming. Well, steaming means we convert your text from the form word context into the original form. Like, let me say, I I did it yesterday, and I do it today, and I will do it tomorrow. Suppose that I have a document like that. So when you pre-process my text and you do steaming, what you should get is, I do it yesterday and I do it today and I do it tomorrow, like that. So what I care is only the original form of the verb, not anything else. Okay, even though you have something like, I have ducks and duck, the plural form will be discarded because you don't care. A duck or ducks will now be dismissed and you only have duck. Okay, so this is also another dangerous operation that you may want to avoid. But right now, looks like a lot of people still prefer doing it. But the more you work with deep learning, the more you see that people tend to not perform steaming. You have to be very careful about steaming. Doing this may remove a lot of meanings inside your sentence, and somehow it will change the whole meanings of the documents, and that's no good. So try to be careful. Okay. Now, when you work with text, they say, well, how can we define or how can we determine the discriminative power of a word? Well, that's kind of a big questions, right? It's like telling people how strong that word be in classification test. Well, it depends. It depends on the problem you're working on. But let's say here in the formula, they provide a very simple technique for you using Gini index. So they say, let's say in your text you have a word W and you have K class level. Now, P and W is the fraction of the document content W that belong to class N. So, suppose that you have class N and PW is the 60%, that means among documents of class N, only 60% of them contain the word W. Well, how do you say a word is strong or not? Well, if that word appear in the class N a lot, then maybe there is a chance that word is strong in classification. Okay. Now we obviously have the constraint like the sum of P and W over every class N should be 1, right? So now what you are saying is very important. If the word W appear a lot in one class and not appear quite often in other class, then we are saying that word has a strong discriminant power. Because when you see that word, you mostly classify your document into class N, right? So that's the whole idea. Now, if for some reason you see that word in the document of every single class, then the discriminant power of that word is very low. Let's say I have a word two, right? And you see a lot of two in any documents, like in sport documents, in social documents, in economic documents, whatever. All of them may contain the word two. And because of that, the probability of having that word in the documents of class N are equal. So we say it's no use, it's no good. That word will not help you in classification process. So we don't care about it. Okay. Um, Therefore, they define for you the Gini index, which is the sum of square Pn. And of course, you may end up with this one saying that, okay, the discriminative power of W here is so high if Gini index is high. Well, it's lowest when the P and W is equally distributed among the class. Okay, it's like it's appear everywhere, so you cannot classify using this word. Okay, so from this, what you see is that this is the criticism you have with this approach. The P and W may bias, right? Of course, it's biased because if the class distribution of the documents is not uniform, like you collect the data on VNS REST and like 80% of your article is coming from like the social topics, then well, most of work you are analyzing will focus on that class, the social class, and that's no good, right? So they propose some idea like why not trying to normalize the probability PN. Well, instead of using PN, we are going to use the QN. QN is the normalized version of PN. And given that, given this formula, you can somehow, for some reason, realign the the distribution of the document class and make your method less depends on the distribution of the data. All right. And this is the new Gini index, which I believe that you can easily get it. And There are some other thing that you may consider in the process, like some information, like information gain. You can also calculate the inhomogeneity of the documents, like this one. It's just like the entropy of the document distributions. And given that we can compute some sort of information like inhomogeneity of a word. But again, let me remind this kind of techniques is very outdated and it's not really popular right now in our world. So you guys may skip this part if you are not so interested in this formula. I don't mind if you remember it or not. It just doesn't really matter to me nowadays. A lot of deep learning models don't consider those kind of measurement. Okay, I just keep the slide for the history of the course. So that's it. And there's some other extra information for you when it comes to tech classification. And well, there are something like mutual information. This one may be very different from what you are reading here in the material compared to the mutual information definition we have nowadays in deep learning. So I don't want to drag you too much into the formula you are seeing in the material. This is just for reference because I recommend you to read about mutual information in deep learning later. It would be more helpful for you guys in understanding how do we measure the correlation between uh, some input data with the feature. Okay, but not like this one. I would like to show you some other example later. Not yet. This is not a good example to me. So take this as a reference. Okay, it's unnecessary for you to remember everything here. It's not so useful for you guys. But anyway, what we have here in the material is that if you can somehow measure the mutual information between the word W and the class N, then you can make some conclusion. If this M and W is zero, then it means the word W is not relevant to class N. Okay. If it is greater than zero, it means the word W is very positive correlate with the class N, which means, you know, if I see some word like ski, for example, if I see the word ski, then I immediately think about a document that related to sport, right? So if that is the case, then the MN of W equals ski is really high. It's a positive number. It say that if you see a document with the word ski, the topic should be sport, something like that, right? Because they are highly correlated. If M and W is negative, then it means if in the documents you see the word W, then most likely that class is not the class N you are talking about. Okay, so for example, in most of document, if I see a word like bow, no, the word bow is so popular. Let's say scientist. The word scientist is very popular in some article related to science, but it's not so related to the document in terms of sport, for example. When you read the article about sport, it's really for you to see the word scientist. And so, if that is the case, if you see the word scientist and you are trying to classify the class sport article, this measurement tell you that the word scientist is not relevant to the class sport. Okay, that's just an example. I don't have the true statistic of that one, so I cannot tell you. But just some sort of way to think about this measurement. Okay, and we have some extra information here, which I believe some of you may interested in checking that one, but not everyone. So may you skip it. Now, the last thing I'm talking today is about Disney. Well, Disney is a very popular method for dimensionality reduction, mostly for visualizing data distribution. Well, I believe that this is very useful for you guys, so I recommend you to have your homework done by reading this Disney. I have a link for the original paper for Disney here in the material, so you guys may want to read that one. So Disney stand for T distributed stochastic neighbor embedding. In another word, this is a technique which is trained unsupervised and it's also a nonlinear technique. It means you are projecting your data onto a new dimension, but in a nonlinear way. It's unlikely that you are finding the projection vector W and you can project your data. No, you are going to perform some sort of nonlinear projection. And what we see here is that most of people are going to use Disney for data exploration and visualizing the data because I think the most important task in machine learning is to observe and analyze your data to see how they distributed in the space and have some proper decisions like what kind of classifier I should use. Okay, and so they are going to use this Disney for data exploration a lot. Now, it's hard for me to explain for you about Disney in the class today. It will take a while, but you must first read the paper. We can come back and discuss about this Disney if you have any questions when you read the paper. But yeah, it's not the main topics that I want to tell you today because it's actually not in the agenda. But anyway, if you want to understand about Disney, what you need to know about is yeah the KL diversion. You have to read about KL diversion, okay? Otherwise, you cannot understand this. And I have the link over there. That link give you the original paper of Disney. You can read about it. Basically, it trying to find the projection key, where key is the distribution of the data on new dimension. And that's that. I hate this one. Sorry. So many phone code that is not so relevant. Anyway, what happens is you have P is the distribution of your data on the original space, and P is the distribution of your data on the new dimensional space. So what happens here is they are trying to minimize the KL diversion, the diversion between two distributions. And what they want to do is finding the projection that give you a similar distribution key compared to the original distribution P. And this process will be an iterative process. Okay, so that's it about Disney. But the detail may be very complicated, and I cannot explain it in the class today for you. So I will have your question answered later. Just keep in mind you must read the paper if you want to understand this one. I guess we may end up with the demo for this job. So wait a minute. I'm going to show you some demonstration. Okay. Hang on. Okay, so as you can see, this is a demo for topic classifications. So they use LDA for classifying the topics. So basically, they are trying to project your data onto a new dimension so that you can classify the data better. Okay, and so you can see this is the correlation between the topics of the text you are reading. Okay, uh, the bigger circle means the higher correlation. So, for example, Union nation is very likely to appear along with legislations program federal. It's something related to the politics, and Peace Nations United and purchased $1 billion. Looks like they use a lot of money, right? So those topics are very correlated. Or here in the purchase billions dollar, yeah, this is like the symmetry matrix or security nation Europe related to tax economy taxes. That's something you can get from the correlation between topics, and also you can see your data as a time series, right? So here is some text, And if you have some text like this one, you will see some sort of different distribution of the data. Okay, so this is the first topics. You can see the distribution of the topics in a time series. See what happens. And this is the topic documents. You can load the documents and you will see what happens with every document. Um, I'm not sure about the detail of this demonstration because it's very different from what we are talking about so far. But the fact is, this demo is used for topic classification and it's used LDA. That's the thing that most important to me. Well, there is also another demonstration that you may want to take a look. Well, this one is the demonstration about the projection of the data from high dimensional space onto a low dimensional space. So what we are seeing is the word embedding of 10K. Okay, and you are trying to project the data onto a lower dimensional space. In this case, it's only three-dimensional space. And you can see that this word embedding is a very large vector. A vector have the size of 200, if I remember. Yeah, 200 dimension here. And because of that, from a vector of 200 value to a vector of 3 value, uh, it loads a lot of information and you have to aware of that. So when you click on one particular word, you can see that the distribution of some similar word is not so linear, right? It's distributed very far away from each other. So when it comes to the text processing, you are dealing with the word and the word has meaning also. When you try to embedding a word into a vector, there's a lot of problems appear. How do we measure the similarity between words as well as how do we making some sort of calculations about the distance between words is remain big questions. Even though now you can use the word to vec embedding or glove or some other advanced representations like the bird or the transformer, all things like that help you represent a word in form of a vector. But in a long run, you will see that this representation has its own limit, and we have to aware of that because the distance as well as the distribution of the data is not like what we are expecting. Okay. May I switch to another data set that is a little bit easier to visualize, for example, MNIST. So you know, MNIST is a very popular data set for recognitions in computer visions. This consists a lot of handwritten digit from 0 to 9, and we can use this PCA to project our data onto a low dimensional space, three dimension, to see how our data distributed on the space. It takes a while to load the data, so be patient. All right, good luck. Finally, we have some data distribution here. So if you observe the distribution of data, you can see that most of data in the same class are gathering around each other, and it looks like using PCA is kind of helpful because right now you can see how your data are distributed on a low dimensional space, but still it's very messy, right? Because now they are mixing between each other on three-dimensional space. That tell you something. You can not use just three dimension to representing your data. That's impossible. But in terms of data distribution, you can use t-SNE instead. So if you are using t-SNE technique for representing your data, you will see the distribution of your data now will be clearer. You can observe it. So as you can see, this is the iterative process. There are RMs trying to find the projection that minimize the KL diversion. In other words, the distribution between the classes. So may I use the label for coloring so that you can observe it better. Still, they need some time to iterate, I suppose. Let me rerun it. Now, if you observe the left side, you can define what kind of distance you want to measure, maybe using cosine distance or Euclidean distance, your choice. Most people care about Euclidean distance, but I think cosine is not bad. Uh, It's a slow process, but in the end, it will show you a very nice distribution of the data. So take a while to converse. It will be good. So be patient. Right now, we don't use supervised thing. We train the T Disney using unsupervised scheme. And as you can observe, most of data which belong to one class now gather around each other. Unlike PCA, right? This one actually feel a lot better. You can change some other factor like perplexity or learning rate. It depends on your choice. Okay. Look like it stopped. Okay, it's run very slow on my computer because it's using the GPU of my computer, and I'm running multiple tasks here, so it's quite slow. But yeah, that's enough, I suppose. It runs quite slow here. I'm sorry for that, but maybe when you try at home, you will feel a little bit better on your computer. Anyway, Disney is very nice tool for data visualization, and I recommend you guys to take a look. Maybe you guys need to use it in the future for data visualization purpose. And yeah, that's gonna be useful. All right. So far, what we are talking about is some techniques for dimensionality reductions, and I hope that you can use this for your work later. It's unnecessary for you to apply those techniques in your projects, but just be aware of that and consider that to be some sort of pre-processing step. So maybe it's going to be helpful for your work. Okay. Right. That's all for today. So thank you for joining, and I will see you next time. Oh, by the way, I will post announcement about the midterm exam later. So maybe you are going to have the midterm exam next week at the same time in our faculty. I will prepare the room. But if you are going to do the midterm exam, you have to do it offline. So I have to prepare the room, and I will make announcement for you when it's ready. So take a close look on the BK e-learning. Okay, stay tuned. All right, see you guys later. I will post some announcement later if I prepare everything for you. Okay, thank you. See you guys later.
See you later.